Hey everyone, welcome back to The Explainer. Today we're jumping right into part 1 of our series on temperature sensors, thermocouples versus RTDs.
We're stepping into the really high-stakes world of industrial temperature measurement. Think about it. Temperature is the most common process variable measured in any plant. You've got standard loops for cooling water or reactor jackets, sure, but we're also dealing with a massive industrial spectrum here. On one end, a sensor might need to measure inside a jet engine or a blast furnace sitting at a blistering 2760 degrees Celsius. But then, on the total opposite end, another sensor has to handle a cryogenic liquid gas tank at a bone-chilling minus 262 degrees. It's a massive range, and obviously, one size does not fit all.
So what happens if you pick the wrong one? Well, the stakes are immediate. Use the wrong sensor, and you'll either literally destroy the equipment, which honestly is kind of the best-case scenario because at least you know it's broken, or you get a silent, invisible measurement drift. And in a chemical or pharmaceutical plant, that silent drift can seamlessly ruin an entire product batch before a single alarm even goes off.
To avoid that absolute nightmare, we need to look at what these devices actually do. At their core, both thermocouples and RTDs are transducers. That just means they take physical heat and convert it into an electrical signal, the process variable, or PV. Because, let's face it, you can't exactly stick a delicate digital controller inside a 2000-degree furnace, right? You need a super rugged sensor sitting right there in the fire to translate that heat and send an electrical signal back to the remote controller.
Now, the real head-to-head difference between the two comes down to exactly how they generate that electrical signal. It's all about the underlying physics. A thermocouple generates a tiny voltage to communicate temperature. An RTD, on the other hand, changes its electrical resistance. So they're basically speaking two completely different electrical languages to your control system.
Let's start with the voltage generators, thermocouples. These guys run on something called the Seebeck effect. Basically, think of it like a heat-operated battery. You take two completely different metal wires, join them together at one end, which is your measuring point, and purely because that junction is hotter than the other end, it generates a tiny voltage. It is a really brilliant piece of physics because it needs zero external power to work.
Because of that simple, rugged build, thermocouples have a pretty unique profile. They boast a massive temperature range, going from minus 262 all the way up to plus 2760 degrees Celsius. But they definitely come with some serious control challenges. For starters, the voltage output is incredibly tiny. A 1-degree change on a platinum thermocouple is only 5.8 microvolts. That's practically a rounding error in standard electronics, which makes them super susceptible to electrical noise. Plus, the output is completely nonlinear. And to top it off, you have to create a second connection at the measuring instrument called a cold junction. Since that junction sits at a varying room temperature, your system has to actively calculate and compensate for it, or your readings are going to be wildly inaccurate.
Okay, let's switch gears to RTDs, or resistance temperature detectors. These usually rely on a pure platinum or nickel wire element. Their operating range is a bit narrower, typically minus 247 to plus 649 degrees Celsius, but man, within that range, they are highly linear and incredibly precise. To measure the resistance change, though, the controller has to send an excitation current through the sensor. And since the lead wires also have their own resistance, you end up needing these complex 3- or 4-wire setups just to cancel out the error. Funny enough, that same excitation current creates a surprising irony: self-heating. Your thermometer can actually artificially heat itself up and mess with your readings if the system isn't designed to compensate for it.
A really great way to think about it is this. A thermocouple is like a tough, disposable pocket ruler. It's cheap, you can re-weld it right there in the dirt, and it'll survive almost anything, even if it's not perfectly precise. An RTD, on the other hand, is your precision lab caliper. Highly accurate, beautifully linear, but fundamentally delicate.
So the big takeaway here is that choosing between the two is rarely just about accuracy alone. In industrial process control, it's almost always about the sensor's ability to actually survive the process. I mean, you could have the most accurate RTD on the planet, but if the process vibration shatters its ceramic insulator in 10 minutes, well, your accuracy is zero. Let's do a quick check to see how this plays out in the real world. Imagine you're designing a control loop for a heavy-duty gas turbine exhaust. It's vibrating violently, taking huge thermal swings, and sitting well over 600 degrees Celsius. Which sensor are you putting in the flow path?
If you guessed thermocouple, you hit the nail on the head. Extreme heat and heavy vibration would instantly destroy the delicate internal wires of an RTD. In a brutal environment like that, ruggedness beats absolute precision every single time.
All right, now let's completely flip the script. What about a delicate pharmaceutical batch process inside a jacketed bioreactor? There's no crazy vibration, and the temperature is a mild 80 degrees Celsius. But your control loop requires exact temperature control to a tenth of a degree because a fraction of a degree is literally the difference between life-saving medicine and a toxic, ruined batch.
For this scenario, an RTD is absolutely essential. A 4-wire platinum RTD is going to give your controller the absolute, highly linear precision it needs for that tight, fractional degree control. The low voltage, non-linear noise of a thermocouple would make tuning that loop practically impossible.
So, just to summarize everything we've uncovered in a quick reference cheat sheet, thermocouples give you incredible range and toughness using that Seebeck voltage effect, but they force your controller to handle nonlinear curves and cold junction compensation. RTDs give you that beautiful, linear resistance measurement for precision control, but they require complex wiring and a stable process environment that won't shake them to pieces.
Okay, so you now know exactly how to pick the right temperature sensor for the job and why you're making that choice. But selecting the sensor is actually only half the battle. Coming up next in Part 2, we are tackling a massive, often invisible installation hazard.
I'm going to leave you with this final, provocative thought. Let's say you've picked the perfect sensor, you've put it into a protective metal thermal well, maybe you even packed it with thermal paste. But suddenly, your loop takes 3 minutes to respond instead of 30 seconds, and it just won't tune properly. What invisible thermal well trap is silently sabotaging your entire system? Think about it, and we'll uncover the answer in our next explainer.
Catch you then.